Good morning my dear friends. Welcome you all to part 2 HVAC technical question and answer video. In this video we will see few practical technical questions and its answer. Let's start the video. So the first question is, we have a condition that air handling unit supplies air to VAV, variable air volume, and from the VAV the air goes to the room. And we see that based on the room space cooling condition, VAV operates. It may be like VAV opens, close, it adjusts, and under partial load in the room, large pressure differential between branches are observed. Therefore, it generates an out of balance system with a large difference in branch pressure, drops and also air flows. So, what will be the reason and how to resolve this one? So, normally in the project site, from the VAV or from the FCU, we will not get proper air distribution from the left or right side and proper air distribution in the project. For example, like you see here, we have the air handling unit which supplies the air to this through this duct to this VAV. From this VAV, I have taken two branches, one here and one this side, and these branches is further going to the other parts of the building. So in this case we don't have equally divided branches here and here. So and here the airflow rate is, for example, 200 liter per second, and here it is 500 liter per second. So this is going further to different parts of the building. It is supplying the air to the different parts of the air. So here this is not done properly equally distributed branches, and sometimes we cannot avoid this type of thing in the site. So the answer here is, ducts should be designed and installed to create a total system with as near as possible. I mean, you have to try to do as near as possible to make the symmetrical branches or at least with the equal pressure drops. So this type of system is easy to balance and keep balanced when the load within the system vary. Okay, because the room load is varying continuously means, so we can easily balance the system and also along the associated air flows. So duct system with the branches that have a very wide difference in pressure differential will not stay balanced and will create large variation in CFM from flows from branch to branch. So for example, like you see here, if you are taking the branch here, we have taken proper equal branches. So in this case the system will be properly balanced. Okay, so there will not be much difference in flow pressure differential. So in the site normally we try to do this type of design, and also in all the site it is not possible. However, we will try our best to make equal pressure drop and equal pressure differential. And the next question is, terminal boxes or VAV boxes or diffuser, it generates large amount of noise even though they appear to be designed and installed in accordance with the all air system guidelines. So generally, if noise is an issue, first we have to do is, in this type of situation, an elbow placed too close to the terminal box or diffuser can increase the noise level as much as 20 decibel. Okay, this is the important case. We have to see the nearby elbow or something near to the VAV or the diffuser. So investigate making corrections to the diffuser or terminal box inlet correction. Okay, so sometime in the at the time of design drawing it will not be there, but when we go to the site, due to the classes with the other utility, we will provide the elbow. So if you have that type of situation, this will increase the noise max as much as 20 decibel. And second thing, if the terminal box or diffuser is oversized and damper have to be throttled very tightly. So this is the important thing. So it will reduce the noise of the system. For example, you can see here in the X direction I have given the percentage of opening of the damper, and the Y direction I have given the noise level in the decibel. So if the damper the throttling is 25% open means, you can see the noise level, it is more than 15 decibel, it is around 16 decibel. If it is 50% open, then the noise level will reach around 8 decibel, and if it is 75% open, it will be around like 4 decibel. If it is fully open, then the noise will be avoided. So you have to follow the damper throttling first of all, and second thing, you have to see the elbow near to the diffuser or air terminal to reduce the noise. And third interesting question is, what is the recommended straight run of duct is required before the VAV, variable air volume inlet, and what is the impact if it is not followed? Keeping 1.5 times duct diameter of the straight duct at the terminal box entrance ensure that immediate entrance is perfectly straight. That means suppose you have a VAV here, and this is the supply duct and this is the return duct, and you should not have any immediate elbow like this. This elbow must be avoided. So that is the reason you have to keep 1.5 times D. For example, in the inlet dia, it is 200 mm means 1.5 into 200. So that distance you must follow. Okay, at the end, because like this you can see here. So 200 mm means 1.5. It is here 1.5 into 200. So 300 mm straight duct must be there before the VAV. Okay, so it reduces the chance of creating inlet turbulence caused by any fittings, whether it is elbow or any other fittings. It will create the inlet turbulence at the starting point of the VAV. So we have to avoid that one. And the terminal box operates like an orifice. So in this sense, this inlet condition to the box greatly affect the output from the box at the selected pressure differential. So normally in the VAV what happen? EAV we have two differential two pressure sensor, flow sensor, one at the inlet, one at the outlet. In the inlet it will measure the total pressure, and the outlet it will measure the static pressure. So difference of these two will make the differential pressure. Based on the differential pressure it will control the flow. So this differential pressure is very important in the VAV. So we have to avoid the before the entrance that inlet fittings, so we can make the proper selection of differential pressure in the system. And the next question is, which type of fan is better, forward or backward curves in the HVAC unit like AHU, FHU, FCU? So you might have seen these two type of fans normally in the HVAC unit, forward curve and backward curve fan. So there is a difference of these two and the selection. Let's see how it is. So normally forward curve fans can be used on small jobs like where low airflow and low static pressure is required. So that means low airflow means you can say that fan FCU. Okay, fan coil unit there where we need the low airflow and also the static pressure also less than 50 pascal. So that type of case we can use the forward curved fans, and don't use this fan for the large airflow. For example, not for the FHU, not for the AHU. And it is generally said that where forward curved fans wheels will exceed 20 inch diameter, their static efficiency will falls very sharply. And also above these wheel sizes, that means 20 inches and above, the static efficiency will go very low. So for the higher airflow and higher static pressure losses, we are using the backward curved fans, and for the small jobs like small airflow and static pressure, we will go with the forward curved fans. What is the maximum flexible duct length allowed? So if you see here, make sure the flexible duct length should not be over 10 feet. And also the greater the amount of sag, the greater the pressure drop in the flexible connection. So regarding the sag and the distance between the type of support, I explained in the last video. The sag you can see, like you see here, the sag is the deflection half inch per foot is allowed. Okay, in 1 foot maximum half inch deflection is allowed for the support, and also the spacing 4 feet is allowed, and the maximum distance of the flexible duct is 10 feet. Between this point to this point, maximum should not exceed 10 feet. And many times due to the obstacles in the ceiling space, we bend the flexible duct in the side. Okay, so this is happening because the HVAC duct it is clashing with the other services. That time we will slightly bend the flexible duct. So this excessive sag creating large resistance to airflow. This will severely make the reduced airflow from terminal box and diffuser. So this is the important thing. So next question is, why the location of mechanical room is important in the initial stage of the design? Because every HVAC design engineer must have this idea before you perform the design, so contractor will not face any issue during the execution. I have given a condition for you to think about the importance of selection of roof and how to perform the ducting in that room. So here you can see we have a mechanical room located in the ground floor, which has the AHU unit serving to the ground floor. So the first thing you can see here is the stair. You can see the stair here at the top of the floor plan. So that is the important and obstruction number 1. So now we are limited to taking all the duct out through the right side of the mechanical room. So we cannot take any duct through this one and here, and we need to take all the duct through this area. The right side, all the supply duct, all the return duct, we have to take to the AHU through this right side of the mechanical room. But we have another issue here. If you see here, let's take a little bit closer look. You can see the red highlighted line. So this is the obstruction number 2. It's a flush beam. So flush beam at the same level of the ceiling hoist around it, shown by the horizontal red line. Like for example, if you see the section of the room, this is the ceiling, That means here we have the flush beam, so it limits the vertical height for passing the duct from here to here. Okay, so this is the important thing. Flush beam image shown in the right side, which limits the vertical space available to move the duct through the duct area to the right side of the room. So now we cannot pass the duct here, and also here also we cannot pass the duct. So we have two obstruction in different places. So to get any duct across it, either you have to go up through the first floor and find a pathway to there. And for example, in this case we have the room here, so we have to create a shaft here. So from the AHU unit, this duct will go to the through the shaft, and supply and return both will go through the shaft, and from there it will go above the first floor. From the first floor again going down, again going back to the this ground floor. From the ground floor it will pass the duct. Okay, so we will have to have some this type of complicated design and very extended design, lengthy design for this ground floor if you don't judge the room in the initial stage. Okay, because for mechanical engineer it is very important. For the architectural point of view, they have given us a room, that's all. Okay, otherwise you have to go under the flush beam, which means dropped soffits that take away the ceiling height, which is practically very difficult, and it will also affect the interior design. So the second case is not possible. Only the first case you have to follow. You have to go through the first floor, again you have to take down for the ground floor. So finally, you need to consider below points for a perfect design at the initial stage for the design engineer. Structural elements like the beam are the most common mechanical room obstruction, but there are others too. Here is a list of obstruction I have given for the initial stage for the design engineer. You have to see the stair, and you have to see the beams. Is there any condensate drain or drainage pipe, the gravity pipe which is passing to that area, so the duct routing is not properly we can make there. And electrical panels and wiring, skylights if there is any skylight, and vaulted ceilings, open to below or open to above rooms, and range hoods. So these are the different cases we have to consider when we go for the initial mechanical room design. And the next question is, a reduction in airflow capacity is observed in the ducted fan system. So what could be the reasons? Although there are several causes of reduced airflow, because you can say like ESP, external static pressure, and different thing. One of the more common causes to do with obstruction in the form of duct elbow preceding the fan inlet. That means an elbow located at the fan inlet doesn't allow the air to enter the inlet uniformly and results in the turbulent and uneven flow distribution into the fan impeller. So this causes the specific system effect, which if unaccounted for produces a reduction in the air flow. So normally what happens is the fan is there, ducted fan, we have to see that in the inlet there is no elbow at the nearby location, because we need to avoid the turbulent, and so you can make sure that we are getting the even flow distribution into the fan impeller. And the next question is a practical question. A contractor followed the consultant design, performed the external static pressure calculation, and procured the ducted FAHU, I mean the fresh air handling unit for a project. After the delivery of the FAHU, due to the changes in the design by the client, duct routing and unit location is changed. Contractor again rechecks the ESP. He observed that he needs higher ESP, external static pressure, and in order to save the delivered unit, he decided to adjust the speed or RPM to achieve the required airflow and to match the ESP. What will be the impact for this adjustment if not properly coordinated with the manufacturer? So generally the fan is often adjusted to high RPM by the contractor because the fan can't provide the required airflow at the design RPM because of higher static pressure ESP. Check the fan RPM and compare it with the manufacturer maximum RPM. The fan should not exceed or above this maximum RPM. The first thing what happened, we need to see the fan is constant speed or it is operated by the VFD. If it is constant speed, we have the adjustable pitch pulley in the fan which will come in less than certain kilowatt, like 7.5 kilowatt. If it has VFD, we can control the speed till 25 Hz. So in your case, if your ESP, external static pressure, is more than whatever the control limit they have given here and still you couldn't achieve means, then it is not possible. Because as you exceed the maximum operating RPM of the fan, you increase the torque, heat and vibration which the bearing are exposed to. So this shortens the bearing life. The only way to cure the premature bearing failure will be to reduce the fan RPM below the maximum allowable RPM. And the next practical question is related to the site. In the chilled water system, after the welding, for the welding is normally performed if the pipe size is more than 50 mm. So after the welding, non-destructive testing is performed to check the integrity of the welding joints. In a design and build project specification, the client didn't mention the percentage of the radiographic testing, and the contractor considered 10% of the total welding joint for the radiographic testing at the time of tender. So project has around 1400 welding joints, and the client chilled water pipe design is based on ASME B31.3, and the working pressure of the system is 16 bar. In the ASME B31, there are different standards are there. ASME B31.1, 31.3, and ASME B31.1 is for the power piping, 31.3 is for the process piping. In the process piping, we have the chilled water system, water, oil and gas, steam, gas, everything is available. So the project design, the chilled water pipe design is based on the ASME B31.3, and the working pressure is 16 bar. So once the project is awarded to the contractor, the client informed to do the testing, I mean the radiography testing on all the 100% joints. So there are around 1400 joints in the project. The project has both the pre-insulated underground pipes and also the building above ground chilled water pipes. So for all the joints, we need to do the radiographic testing as per the client information in the later stage of the award of the project. So it will increase the project duration, since when we perform the RT radiography testing, the nearby area is protected and no work should be performed. Okay, so that time we cannot perform any work, so it will increase the project delay, it will make the project delay, and also it increases the cost for the contractor. So what contractor should do at this condition? Because in the project specification it is not mentioned, and they followed they just assumed that 10% RT we have to do. So but now the client is insisting them you have to do 100%. So what the contractor have to do to protect himself and to avoid the cost and the delay of the project. So if you know the answer that how to decide this one percentage of NDT, like RT or UT, whatever it is, and just don't forget to add your comment in the comment section, and the answer for this question I will start from the next video, part 3. Thank you. Bye bye.